So, good afternoon, everyone. Good. Wow, it's really humbling to see a full house. Well, thanks a lot for desiring to spending the next 30 minutes with me. So my name is Venkat Venkatakrishnan. Like how I was introduced, I'm a database engineer by profession. I'm not a developer or an AI engineer. That's a disclaimer. Very pertinent to what we're going to speak for the next 30 minutes. Well, I love technology, anything related to technology, and also I read a lot of colonial history, and I also listen to a lot of music, and that's what you see here. I purposefully put that word melomaniac so that people, it raises all your eyebrows thinking that I'm some mania, but it just refers that I'm a connoisseur of music. Of course, I like to read a lot, love camping, hiking, spending time with my friends, and I don't know if I could say this being in Durham, I'm a Tar Heels fan. So, sorry. Go Tar Heels, sorry. Duke and Wolfpack. Anyway, so those are fun facts about me. So this is a very high view of the agenda that we have today. So I'm going to, being a database engineer all through my career, I just want to harp on what are the traditional RDBMSs and how they are placed in this entire data infrastructure landscape, and what are those limitations inherent within the traditional RDBMS infrastructure that warrants something like vector database. Of course, I'm going to also take you through a very high level of the high school linear algebra about vectors, and of course the vector database, its principles, and how it fits in the entire AI engineering landscape, and few examples of vector databases here and there, and hopefully if the time permits, I will also try to do a small demo which I prepared for this one. It's a very poor man's AI, for lack of better terms. That's possible by a DB engineer. So. Yeah, I think we all know how we are all techies, and so the traditional RDBMs have been there for decades now, and we all know how they have been so vital in powering so many of our mission critical applications, our businesses, whatnot. Right, so they store data as columns and rows, and a lot of attributes of the data that we are wanting to store. The features and the attributes are stored as columns, and the data themselves are represented as rows. And of course, they've been time tested, right? Like we said, they've been in the business for so long, and there are so many plethora of options that we've had over all these years, not one or two, catering to each application need, and there are so many vendors who have been extremely successful, and there are so many businesses in the entire world who have benefited greatly from these databases, from these technologies. So, of course, they help us in transactional processing systems, the OLTP, OLAP, the data warehousing, reporting, whatnot, right? So, and most importantly, the reason why they have been so successful is because they always ensure the integrity and consistency, the asset complianceness, which is what makes them the backbone of all the business critical applications that are running throughout this world. So now, why vector databases, right? So with all these, the RDBMS that we just spoke about, they enforce a very rigid schema structure, right? So, and of course, with all greatness, there is always some kind of drawbacks here and there and limitations. And RDBMS are no, they also have their own share of limitations. One is which is because they have been designed to be rigid in their schema structures. So, and that's why they lack the flexibility in handling any non-structured or unstructured data. But we have evolved in this modern world and the modern applications and the tech stack that we've been developing. We have had so much of complex unstructured data, even the click streams, the videos, audios, text, images, whatnot, right? All these are all, the SQL databases are not designed to handle. Right? They are not equipped to handle and manage, store, or retrieve whatever that they are designed to do. The storage and retrieval is not part of their functionality, so to speak. Of course, the NoSQL databases can handle them, right? That's why the SQL databases, they got evolved into, there are a lot of players that came into the market, like MongoDB, which could beautifully store the document databases and retrieve them efficiently. So the NoSQL databases could handle the unstructured, semi-structured data as well. But should we restrict the databases just to store and retrieve alone, or could we do something more than their traditional functionality, right? Why not? Sure, yeah, why not? If we have more capabilities, why not? And I think that's where the vector databases pitch in, right? So how about if the databases also have the power of comprehension, so to speak, right? Besides their traditional storage and retrieval. Yeah, so now welcome to the world of vector databases, which is really fascinating. So what these vector databases are going to offer, right? And how are they different from the traditional RDBMSs? Well, when the traditional RDBMSs are going to store the data as rows and columns, they're going to put the data in the high-dimensional vector space. Now, why should they do it, right? So that's the most pertinent and intriguing question that everybody should ask, right? Why not rows and columns, or why in high-dimensional vector space, and how that is going to help us in designing, highly efficient AI-driven applications. So I think that's where the next point comes. It enables, right, this efficient similarity searches and semantic understanding, allowing all these AI-driven applications to retrieve the data based on the meaning rather than just an exact match. So for example, right, if you have a SQL database, you're going to write a beautiful SQL query and have where predicates to do exact matches, right? You have an ID or some other column where you go against that table, the data, and then you're going to retrieve. So that's going to do an exact matching of what you're intending to extract from that database and the tables. How about, whereas with vector databases, you don't have to do an exact matching at all. You can do an approximate matching, and you don't even need to write any SQL queries. You don't have to be trained in SQL language at all. You could use natural languages, right? Like how we speak now. How many audiences were there? How many people were there in the audiences during this presentation? On the All Things Open. So that's a query you could issue. And if there was a database which is going to a vector database which if it has had all these data points stored as vectors, it's going to determine, say, yeah, there were beautiful 50 faces here, 50 people who were sitting, in this particular auditorium during this time. So things like that. So, and of course, the example is you have image searches, the product content recommendations, the natural language processing. These are all very good examples where the vector databases could be used efficiently. So this is what I was telling earlier about a little segue into what are vectors, just to refresh the linear algebra from a middle school and high school. So we all know that vectors are nothing but mathematical entities with both, it contains magnitude and direction. You could represent the vectors as arrows pointing in a certain direction, with certain length. And most importantly, it can also be represented in terms of arrays with either integers or floating points, where each of this number is going to correspond to a specific dimension or a component representing what that vector's attributes are. So here in this example, consider these two vectors wherein one is with an array of 1 and 5 and the other one is with an array of 4 and 2. So these two numbers represent a component of the vector in that dimensional space. In here it is a two-dimensional space. So now let's carry this forward, the concept of vectors, let's carry this forward to the realm of databases. Now how could we apply this? So these vectors can be used to represent the data points. And they can store the numerical representations of the data in the form of high dimensional vectors. So for example, apples, oranges, or men, women, flowers, fruits, these are all data or the data points which can be represented in a numerical form, and they can be converted into numerical form, and they can be stored as vectors. And these vectors are nothing but mathematical encodings of various types of this unstructured data, just not the text alone, the documents, the unstructured data like the images, the audios, videos, everything, right? All these could be encoded and converted as vectors, and they could be stored in the vector databases. Now, how do we do this, right? On a high level, yes, it's pretty clear. Yes, we want to vectorize the data, regardless of its structure. And now, how do we do that? So, this is where the power of the vector databases really enthralled me. So imagine a data set, right, with each data point having various attributes in the vector database. Now each of these points become a vector, and their attributes are converted into numerical features that form the components of the vector. So it's just not that data alone, not that data point alone, but the attributes are also being stored in the vector database, right, as vectors. Now, why is this important? This ability of having to store the components and the features and attributes as also the vector as components of the vector enables us to capture and maintain the semantic relationships in the context. So this is where I would love to say that it unleashes the power of the vector databases. So it's just not to harp on what we spoke earlier regarding the difference between the exact match and any ambiguous query, right? So in SQL databases, you'll have to have exact matches in order to retrieve the information that you require. With this power of having to embed and encode and store semantic relationships between the data points, it could be millions of data, right? It's just not, we're not talking about a handful of data. We are talking about millions and billions and trillions of data. So now, if you are able to capture, just think about it. If you are able to capture and maintain these semantic relationships and embed them into the database, it provides us an enormous power, right, to search queries and which can retrieve approximate neighbors. It can do semantic searches, and it can retrieve lots of information that's going to be pertinent to design and develop intuitively responsive and personalized user experienced applications. So that's where the power of vectors and vector databases are so crucial in the AI space. So moving a little further as how this is going to happen, right? So there's a text, which could be, just think of it as, I just gave it as text. It could be any unstructured data or anything. Then the first thing that we want to do is we want to vectorize, right? We want to convert that data in forms of numerical representation as vectors, which is what is being done by this embedding model. So we'll come to that a little later. And that embedding model is going to vectorize that data, and it's going to represent it in forms of vectors, which can then be ingested into the vector databases. Now, so we harped a little on the semantic search, right, and how the vector databases are helping us to perform those semantic searches. And that snippet, the picture on the left, it helps us understand what exactly a semantic or a syntactic searches are, and which could establish a context. So for example, we say there's a dog and there's a puppy. So now we as humans, we understand the difference between a dog and a puppy. But we want the technology, which is the databases, also to embed this meaning and context between what a dog is and what a puppy is. Whereas in a regular traditional RDBMSs wouldn't know the difference. They are just going to retrieve a dog separately, and it's going to retrieve another row which has a puppy as one of its data. Now, whereas vector databases have the power to understand that, yeah, dog and puppy are kind of meaning one and the same, right? And those are the examples given there, right? So there are two similar vectors. So the striped blue shirt made from cotton, and cotton made maritime shirt. Now, these two almost make a similar contextual meaning, and when they are stored in the vector databases, they are stored kind of closer to each other. So when a user runs a query, or he wants to understand, or he or she wants to understand, or runs a query against an application, it's going to do a semantic search and run an approximation. It's going to pull all the relevant data which are in that proximity clusters. Now, even though here, in the right side, we have a similar embeddings, how they are stored in a two-dimensional database or vector space. So it has the ability to cluster the data which has similar meanings, right? Which could be used in a similar context. And they're going to position them so that, why do they do it, right? Why should they be all closer together, right? The answer is simple, because we need faster retrieval times, right? So we just want to adhere to the law of physics. We want instantaneous responses for our applications, because that's what is going to give that enriching user and personalized experience for anybody that's using or consuming that particular application, right? Now, so we spoke about the embedding model there. Now, there are many embedding models. There are so many. There's amazing research that has happened over the period of many years, and one of the popular embedding model is called as BERT. And here, once again, right? So this is another amazing example of what context means, and how it could. How this vector databases could help us in establishing the context, right? So here the word right is used in 3 different ways, right? Right? Yeah. So your answer is right. And then turn right at the corner. Everyone has the right to freedom of speech, right? So now, how do we make the technologies to understand the context and the relevance of where it was used? And that's what is done by the transformer encoded model called as the BERT, which is once again going to represent and vectorize each of these words relevant to the context, and is going to save it as is. Now this is going to give us an oral picture, right? Just to augment what was shown earlier. You have disparate data sources, regardless of whether it's images, documents, and audio. Of course, in the practical implementation, you may not have you could have individual databases catering to each of your data type that you want to really vectorize. But here's just a very high-level example. Each of these data points, they get into the embedding model, they vectorize the data, and they store in this multidimensional space, which is going to be stored in the vector database. So let's take this a little more further and see how, now that we have done the job, right? So as how we do it in a regular data infrastructure pipeline, you have data from disparate sources. Either you capture them, you process them. There's a pre-processing happens, and then you eventually load the data. Now let's focus on the application, right? And it's interesting that application, when it sends the query, it still sends that query to the embedding model, right? It doesn't directly query the database, because the reason being, we want to vectorize the query as well. So whatever the natural language that the user is trying to determine, using whatever result or whatever data that the user is trying to accomplish or determine and retrieve, he or she is sending in their own natural language. That query is also going through the same embedding model as how it was initially vectorized. And then it goes through the same pipeline, and then here it does a semantic search, and then it tries to run a lot of matches. So there's billions and billions of vectors that are stored. Now it's going to go against each of these vectors, and it's going to determine where approximately I can fit this guy's vectors, and then it returns the results, query results, to the application. Now, I also loosely mentioned that it can go against all the trillions of vectors, which we know that is not efficient, right? We don't want table scans. We know how hard it can be, how bad they could be. So now that's where the concept of indexing comes, like how it happens in the traditional RDBMSs. So even the vector databases have even powerful indexing strategies that makes this search really, really efficient and faster, and which is once again going to augment and enrich the user's experience, because we want everything happening dynamically, and we want things to happen instantaneously. So this is the reason why I wanted to put this particular slide is everything is the same, except the fact that there's also a metadata, right? Now, the vector databases, they just not only vectorize the data and store them as embeddings, right? So let's say that you want to query the vectors. Nobody wants to query the vectors directly, and if you want to run a search and see a bunch of floating point numbers, it doesn't make any sense to the user, right? Instead, what the user needs is the actual data, right? So the vector databases, besides storing the vector embeddings, it also stores the metadata and the raw data. So that's where it has the ability. So it's the best of both worlds, right? So it knows the metadata, it also stores the actual data, then it has the vectorized data as well. So now it can easily, through the semantic searches, it is able to retrieve that original data to the user. So for example, I guess each of us, right, each of us have Google Photos, right? And Google Photos, it says, it retrieves memories for us, right, everyday memory, right? And then it says, I'm not sure if Google Photos uses vector database as the background, because they are very privy about it, but I'm trying to understand, trying to relate the concepts here, right? So you could run a query on the, you can type this on the Google Photo saying that, get me the photos from maybe last April of all the images which are having mountains, right? Just throwing something like that. So now, it's not only going to, if it just retrieves some vectors, right, and floating points, it's not going to help us. But it's also going to give us all those photos which match what the user is expecting the application to retrieve, right? It's just not going to be one. There are going to be multiple. Okay, so this is probably an attempt to put everything together and arrive at a holistic, overarching architecture of what vector database could do and could not do, and what happens, if you do not have that. What happens if you do not have a vector database, and what happens with the vector database, right? I think that's what we established. So I'm trying to not jump guns here, but without we all understand that the large language models have there's some cutoff time for them, right? I'm not sure how many of us would remember, last year when ChatGPT was initially introduced and it became quite popular. If you're running some query, if you're running some, if you're trying to chat with it, it will say, I'm retrieving data as of this particular date, right? So it doesn't have any knowledge about the current data, right? And if not, it's going to hallucinate. And then it's going to just throw some junk, and there are a lot of people who believe them. Now, with and that's a limitation of that LLM. Now, how the vector databases is going to help us here? So once again, the same pipeline, the data is there's a chunking process that happens. It's embedding model. It stores. Then from there, from the application, somebody is prompting, and then it's converted to a query, and then it goes through the same embedding model. Then it does that approximate near neighbor search space, and it is able to position the query vector to the actual data, and then that data is retrieved, and then it goes through another model where it is re-ranked based on the score. So if it retrieves 10 to 20 results, it still goes through a sorting algorithm, and it re-ranks based on which could be the most fitting output, what the user is expecting, and then it sends to the LLM, where it also helps to generate and then sends the data, the output to the user. So I think we all know this is called as the retrieval augmented generation, right? So this is one of the key areas where the vector databases are so helpful, in the AI-driven applications. A quick time check. Do we have?
Yeah, we have a few minutes.
Oh, okay. Oh, okay. So I don't know if I have enough time to go through everything, but so let me talk about probably these are the vector databases in the market today. So some of them on that quadrant, on the left top quadrant, they are the dedicated vector databases, so to speak. Of course, you also have the PostgreSQL, MongoDB as Atlas. It has the PG vector extension, and of course, the most popular one, and also it also is commercialized and enterprise offering is, as I know, is Pinecone, which also offers it's a fully hosted environment, and they take care of everything. So I have my demo in Chroma. It's a lightweight. I don't know. So let me probably stop here and try to go to my. So here, what I'm trying to do here is I have a bunch of random sentences in a CSV file, and I'm trying to run it through, insert that data into using this embedding model called a sentence transformer. I'm trying to add it to a Chroma database here. So let me run this quickly. Oh, sorry. I didn't realize. Okay, how do I switch? How do I switch? Why is it still not working? Okay, there you go. Sorry about that. Okay. So let me quickly run this, guys. So this is where I was mentioning about this sentence transformer. That's the embedding model I'm planning to use. So let me run and initialize view. So I'm just going to ignore that warning message. And this is where I already have random sentences generated in the CSV file, and I'm going to create a, using the pandas library, I'm going to create a data frame out of that. And then here is where we're going to chunk. So the chunking, it's not really necessary here, but I just wanted to give you a handle of how it happens in when it comes to AI space. So the chunking is nothing but a way to, if there are long paragraphs, then chunking helps you to split them into definite sizes into smaller parts, so to speak. And here we initialize this embedding model called as a sentence transformer. And then, and this next step we are going to, so in the collections are nothing but, if you want to, they are synonymous to tables in databases. So here we're going to create the collection on the Chroma database, which we previously initialized. And then here's where we're going to run an upset operation wherein all the data or the embeddings. So if you recall what we said earlier, so every data, it gets vectorized into embeddings, and that's what it's going to happen in this particular step, where you create, using that transformer model, we're going to encode and create those embeddings in this step, and also not only embed and then ingest that data into the vector database. And here's where the fun part comes. We're going to run a query and see what it's going to retrieve. So it was a haunting night. So that's the query that the user is saying, right? And then it does that semantic search that I was talking earlier, and it is retrieving these sentences that match the sentiment, what was expressed, and the context, right? Those are those 5 sentences. Now, let's try to tweak this a little bit, right? So let's say it was, okay, since I like music, let's say it was haunting music, right? And let's see what it retrieves. So now you could see, right? It has a different, it retrieved different data, right? So now it understands what haunting really is, right? So earlier it was telling me, it was retrieving all the sentences which was expressing the sentiments which were related to anything haunting, like this particular sentence here. If you're looking at the third sentence, right? this was the first, I guess this was one of the first sentences that was retrieved earlier, because it understands the semantics of it. Now it has retrieved as the third sentence instead of the first one, right? Now, let's see. Once again, with music. So once again, now it's a completely different set of results, right? So now you see that a sudden flash of lightning will be the dark side. Now it is, so this is where the re-ranking happens, and it is trying to provide data which it thinks is closer to what the user is expecting, right? Okay. Well, thanks a lot.